Cognitive flexibility is the ability of humans to understand and work through new and unexpected conditions through senses, experience, and thought. Now, cognitive flexibility can be shown in bumblebees in experiments done by Lukola, Perry, Koskos, and Chitka. They performed two experiments. These experiments show that bumblebees can adapt to unexpected conditions in the environment for a reward.
In order to test the cognitive plasticity of these insects, bees were presented with the task of moving a ball to a particular position in order to obtain sucrose solution, a reward for task completion. This test to unveil bees' learning intelligence was carried out over two experiments. The first sought to explore if bees could learn to accomplish the task in general. This was done by testing an experimental group of bees who witnessed a plastic model carry out the task against a control group who saw no demonstration. The second experiment aimed to examine the impact of social learning on task performance. In this phase, three groups were examined. The first witnessed a demonstration of successful task completion as performed by a bee pre-trained to complete the task. The second witnessed successful task completion as a result of magnetic movement of the ball to a specified location. The third witnessed no demonstration.
Prior to testing in Experiment 1, bees were trained to move a yellow ball to the center of a circular blue platform with a diameter of 7 centimeters. 10 training trials were conducted as follows. The bee was tasked to move a small yellow ball to the center of a blue platform in order to receive a sucrose reward. If the bee did not succeed in 5 minutes, the researcher used a plastic bee at the end of a stick to move the ball to the center. Bees that didn't succeed at least 60% of the time were taken out of the study. Following training, 10 experimental trials were conducted. All 9 bees that participated in the experimental phase were successful in all the trials. In addition to being successful at moving the ball, bees also demonstrated complex learning abilities. With each successive trial, bees took less time to accomplish each task. In Experiment 2, bees were trained on a platform with 3 lanes. Each lane had a ball at a different distance than that of the adjacent lane. 3 different categories of training occurred to explore the effects of social learning on bees: social demonstration, ghost demonstration, and no demonstration. In social demonstration, a trained bee demonstrated to an untrained bee how to move a ball to the center of the platform and reach the sucrose reward. The pre-trained demonstrator bees were trained on a platform in which the 2 closest balls to the center were glued down. In ghost demonstration, a hidden magnet was used to move the ball to the center of the platform. Bees who received no demonstration found the ball already at the center of the platform with the sucrose reward. In addition, a generalization trial was conducted. In this trial, the ball closest to the center was black, not yellow, allowing researchers to rule out the attraction to color when moving the balls.
On this figure, we can observe the paths that the bees took, from the origin, which is the place where the ball was placed randomly, to the hole, where it needs to go, where the reward is. We can observe that the bees reach their goal, but it takes them a little while to get there. This figure shows the bee's path on the last trial. We can clearly see a faster and more direct approach. On this graph, we can observe on the x-axis the demonstration group, and on the y-axis a proportional success rate. On the graph, we can observe that not only did the bees figure out what to do, but also we can see that most of the time the bees would approach the nearest ball instead of the farthest or the middle ball. This graph is similar to the one we saw before, but in this case the nearest ball is black, meaning that the bees did not respond to a color, but to the nearest ball in order to receive the reward.